so I'll answer it to all of you. The question was, why was I going on about this being at the boundary, this embedding? So I want to say, I don't need any of that boundary stuff just to have an embedding like this, and just for it to give me a functor. That, I don't need to care about the boundary. When I need to care about the boundary is when I'm trying to make this product, right? So say I have some other skein already in here. It ends somewhere down here, and it's doing whatever. What I need, if I'm trying to multiply, is I need some canonical way to get all of this out of the way, so I can add my next skein. And what we do is the fact that at this boundary I could, blue is my defect color, I won't use blue. I could just take my surface and sort of retract it away from the boundary like that, and then I can embed this disk. And so whatever my new skein is, I could put it, in this disk for a little while until I'm out of the danger zone, and then it can do whatever it wants, right? But I needed to be at the boundary in order to make sure I have space to put it in. So the takeaway is the boundary stuff is only necessary if I want an algebra structure here. So what I would like to do during these lectures, I want to define an example of one of these defects, and I want to tell you what these internal Skein algebras look like, what a sort of presentation is for them. And then after that, we'll talk about sort of the geometry behind this. What was the geometric motivation for me, at least? Okay. So, what I need to do is I need now to define one of these for you, using actual categories and not just the letters A, C, and D. Now do I do that? So let me just write. Example. Is this is this business? And what is the functor I'm going to get? Well, here, let's call this iota. And here I'll call this pi. And a reductive group, I can think of it, write down a presentation with generators. I'll say EI, FI, KI. These are generators for a reductive group. And here I'll say B, I'll just think of it as the EIs and the KIs. Right? So it's including just these generators here. And then this map will be EI gets sent to 0. So this is what pi does, and iota just goes like this. Okay. So that's what I want to use to build my defect. And what is the defect going to be? So we'll take a category rep QG. So this is going to be, it came up in the first lecture, a braided deformation, the category of representations of G. I'll take my box tensor, rep QT op. So this is braided opposite. And I need to go to the Grunfeld center of rep QB. So here I'm going to be looking at representations. Here I'll be looking at just integral weight representations. And here I will be looking at representations of B that restrict to representations of T. So I'll be looking at some important part is just representations of these things. And what is my functor going to do? Well, I'll do V box tensor chi. So now on, I'll try to write chi for representations of T. So they're also called characters. And what this is going to be sent to is, well, I want to use this embedding and this quotient. So it'll be iota star B. Now this is going to be starting in rep B, so I can just take the tensor product in rep QB with the pullback along the embedding, and then here, half rating, we won't need it, but just to make our notes complete, the half braiding is going to look like this. RG. So, where this notation, this whole thing, where this is the R matrix describing the braiding in rep T, this is describing the braiding in rep G, and this just permutes the factors of the tensor product like that. So this is my example that I want us to focus on for a while. And let's call my Skein theory parabolic. So all of the sort of algebras and categories, everything I can build off of this, I'll just call it parabolic Skein theory in general. So, first question I want to ask that I think helps gets us oriented is what can happen at the defect. Right? So, my objects are all built up along embedded graphs that are stratified and they can meet the defect, like this. Let me make sure I do all the orientations the same way in my notes. So F. Mu. All right, so what's going on here is I want to consider these are both highest weight representations, and their weights are given by lambda and mu. So for SL2, these would just be two numbers. And what I want to ask is what can F be? Right, what could I put here? And so F is, well, first, in the last lecture, I mentioned that F is going to be a morphism in rep cube B, this defect category. So, and in particular, it's going to be the morphism from this V lambda tensor I mu to the identity, right? And this thing is just what I said above. This is this inclusion and product thing. And what I want to say is what can happen how I'm going to figure this out is I'm going to say, well, I have, because it's in rep QP, I have an action of EI and KI, and I want to know what does this imply. So if I have some EI, I'll just drop the subscript for now, and I'm evaluating this on some element here. Well, because it's a morphism in my category, I need this to equal, I need this to be linear, so E acting on V tensor alpha. Right? Okay, so here, this one, if I'm acting on a tensor product of representations, right, this is going to have to be delta E acting on V tensor alpha. Right? I'm paranoid always about messing up computations at the board. So let's think about what this thing is. Delta E acting on V tensor alpha. Well, this is going to be EI V tensor alpha. So here it just acts on the first one, and on the second one it's going to be KV tensor E alpha, like this, right? Here, this is going to be 0. Because alpha is coming from up qt. Minus 9 of chi. And this pi sends e to 0. So that has to be 0. So on the inside, I'm going to get this, whatever this is. What has to happen on the outside? Well, f lands in the trivial representation. So E acts here by 0 anyway. So I also have f of v tensor alpha equals 0. Right? So together what this implies is that f of v alpha equals 0 unless EV equals 0. Right? So for the only way for the action to agree before and afterwards is for this either to be 0 or for it to be killed in E. So what we get from this altogether is we conclude that f has to project onto the highest weight space. Which is to say, f has to project onto the kernel of E, and if I had multiple E's, it would have to project onto the shared kernel of all of those. So this is quite, just to have a non-zeromorphism here, it's quite constrained already. Right? So I think this is seeing this computation is maybe the first time where you might start thinking that adding defects could in fact simplify the story, right? Because we have very few choices here, and the Skein theory here will be much simpler. So that's one part of the computation. What's the other part of the computation? Well, maybe I can do it here actually. I also need k of f v tensor alpha acting like this to be k of this delta k down v tensor alpha, like this. Right? And here, this is just going to be f of v tensor alpha, right? Because whatever this morphism is doing, it has to land in the trivial representation, and so k is going to act just by multiplication by 1. So here, it has to be this. And here, this is going to be f of kv tensor k alpha. So k can act on v, it could be scaling by anything, but I happen to know that the only thing that matters is the highest weight vectors, the highest weight vector. Everything else is going to get killed anyway. And then this chi was a one-dimensional representation, so what I'll get is that this will be f of, what letters did I use? Lambda mu, v tensor alpha, and this is just linear, so f of v tensor alpha, like this. And so what I see is actually that this has to equal 1 for these two to be the same. So I also get that mu lambda equal mu inverse, like this. So what we conclude is if I'm drawing my skeins and I have a skein that passes from this G region to the T region, I know what the color has to be, right? And I know what the coupon has to be up to a scalar. So it's really quite restricted in this case. Okay. Let me just write that down. Write it down at here. To conclude, if I have this situation, make sure I write my orientations the same. So here, I'll go up. Now what I want to do is I want to translate this whole thing into, I'll change the orientation here. And that's going to, here the computation was easier than was pointing in, but what that orientation change will do to this requirement is it will require that these are the same. So what I see is this is only non-zero if lambda equals mu. Are there questions on this? Now what I want to do is make it even more concrete and say, now that I have this, what I'll do is I'll think about this GSL2, which is a case that's been studied quite a lot historically and still now. And I'll say, what do my internal Skein algebras actually look like? So, and how so this is a Kaufman style. Representation for SL2C. Okay. Yeah.
Is it mu or mu minus 1?
Oh, I changed the orientation. So it's if it was oriented in, then it would be the other way.
With a 0 of
Yeah. So I have here, so the question is why did the sign change? Which is a super reasonable question. The thing that I was using is that, is this. That when I take the dual, I take the business of that, and then also that this mu equals this mu inverse. Like this. So those are the two things going. Okay. All right. So let's just think, we'll recall first what happens with the G skeins. So one, I will say, important fact. A lot of beauty behind it is that we can always color by the fundamental representation. And if you haven't seen this term fundamental representation before, this is, well, we think when we describe SL2C to each other, we just think of it as matrices, 2 by 2 matrices. So it's that two-dimensional vector space that it's acting on. So it's acting on C squared, and I'll just call it just V in this part of the discussion. Okay. So this is one important fact. So maybe important facts, one. And the second important fact is that V and V dual are canonically isomorphic. So we don't need orientation. And this is why, so together, what this means is that I'm just going to be considering unoriented skeins. And when I want to write down the relations for those skeins, what I'll get is just, if I have a crossing somewhere, this is all colored by D. Oh, I was doing, I know it's not important, but I was trying to do them all in yellow. Like this. So this will be just equal to, I will not get the Q's messed up. Oh god, I gotta look twice. Like this. And then the other one. Like that. And then I also have, if I have just a curve that's contractible, I can get rid of it. I'm giving up on the yellow green. It's already missed it. Like this. So I have this relation. I also, I did a bit of work to explain gates so that we can have things going near the boundary, curves that don't open, or that aren't closed. So let's say I have a curve like this, and this is somewhere where I had embedded a disk, and I'm keeping track of the fact that my algebra was induced by embedding that pushed a disk just right here. So what's this going to be equal to? This will be Q 1/2 plus Q to the minus Q to the 5/2 minus plus minus. So what's going on here? Here, there's something going on is we have this extra data called states. And it comes from the fact that when I was writing down an expression for actually what does the internal Skein algebra look like, I wrote down something like this. And here's what I was focusing on, because this is what gives us tangles. But here, we also had this little term, and this is what's giving us this little information. So these are both going to be referring to elements in this representation. And I'll just use it to be the highest weight and the lowest weight representation. So that's my notation. These are both vectors. So I've got Skein relation. I have this one also. Minus plus. So if I come in a gate and I go back and I'm plus minus, this will be this. And this, the things are the same, it will be 0. So if you actually found yourself in dire need of making computations, this is what you would use. Understand. So this is the G-Skein theory part of it. In general, my surface is going to have G regions and T regions. So what does it look like in the T region? So let's do T. So T is the maximal force in SL2C. So I can understand it as just diagonal matrices. And then in C star. And I think of this as just C star. So now let's consider this part. And the tensor product in this category is going to look like this. So it has a nice expression in terms of the weights themselves. So what I'll do is I'll just color by lambda plus 1. Like this. I'll say I've done something horrible. I've switched from multiplicative notation to additive notation. Sorry, everyone. So I'll color by this, and I'll use the fact that if this is chi plus 1, then this equals chi minus 1. So if I take chi plus 1, I just switch the orientation, I get minus 1. Like that. So there's that. This is one-dimensional, so up to a scalar, I only have one choice of state. So I don't need to put any of these on. So there's that, and then there's no compactable choice of state. So it's one-dimensional. All right, and then what do the Skein relations look like? Well, I still have a crossing, T, like this. And what this is going to look like is q to the minus 1/2. First one going up, that will be q to the minus 1, the other crossing. Like that. So this will be one of my Skein relations. You can already see that if I had some complicated tangle, right, it's going to be much easier to work with on the T side than on the G side. So I have this, and I also have my gated relations. I'll draw them after. What's going to go on here? So if I have this, like this, it's going to be, so if I'm near a gate, I can enter it or not. And there will be the other direction too. Okay, so those are all the relations in the T region. The final thing that I need is what happens at the defect. I'll have three relations. Like that. And what will they be? So if I'm up here in the G region, and then I cross down here, all I need to pick is the orientation. If it's this one, then I'll be 0. And that also implies if I come down here, this will also be 0. And in fact, if I try to go up like this, that will also get 0. So we see actually, it's quite constrained what can happen at the defect. If I just try to cross it in not the perfect way, I'll end up, vanishing, leaving 0. Okay. Are there questions on this?
Can you say which one is G and which one is T?
Yeah. On top.
The arrow going up would not be 0.
Yeah, the arrow going up is not 0. But I think if you saw these, you may think that actually what I've done is made two completely separate Skein theories that don't talk to each other, right? If passing between them is so dangerous, you usually end up being 0. That doesn't seem like there will be a lot of communication or cultural exchange going on. So I'll say how actually does it look like to have skeins move across the region. And it turns out that actually isotopy does a lot of the work for us. I'll just give an example of how this can happen. And I think maybe a computation will do as well. So let's consider an annulus with a defect. I'll have the inside part be t, and the outside part be g. And for this example, what I want to consider is I have this skein passing between the two regions. Make sure I get the structure right. And this skein going around. Is this clear what's happening? So this is, so just already drawing this, I know that this has to be oriented like that, right? And what I can do now with these two things, so what if we name these? I'll call this one A, and this one maybe L sub G, because it's some loop, but it's in the G region. What I can do is I can resolve this part using just the coffin bracket skein relations here. And let me just draw that out. I'll just draw all the circles that we'll end up getting. Okay, so here I will resolve this crossing. What I get is, well, one resolution will go like that, and the other resolution will go the other way, like that. And now, what I see is actually I can move where this crossing happens, and I can sort of dip the whole skein into the T region, right? It's just a matter of isotopy class where it passed from one side to the other. So I can actually move it all the way inside, like this. And I can get back this thing, that. And this will be, I'm going to try to draw the, and this factor and this factor. All right, and so where did the q 1/2 q minus 1/2 go when I did this? Well, I can slip it in, and then I have a little t crossing here. I have something that maybe looks like this. And so when I resolve that, and then I apply this relation, I'll end up getting just this thing again. So what we see is that I take A, LG, this is going to be equal to A, the same skein, plus L, we can call it T, LT inverse, like that. So you see we do get some way of moving things between regions, but often I need some scaffolding skein to sort of escort them across the boundaries. All right. Are there questions on this? So we've built a bunch of sort of elaborate algebraic objects using some nice category theory. What I want to do now is talk about sort of the geometric reasons behind this, and sort of what happens when you start to consider this with just like rep G and rep T, what's going on. This. Okay. So here's the idea. Is when C is just rep G, we're discussing character varieties and stacks. Okay, so this is the thing I will make precise coming to lectures. And when D, the defect, is just rep G, box sensor, rep T, going to the Dinfeld center, the rep T. So when I introduce the defect, but I don't have any definition parameter, I'm just working with the classical things. We're discussing what are called decorated character varieties. Okay. And what is this decoration? This just means we have some additional framing data. So I want to talk about what these things are and why this is true. Here's a definition. The G representation variety of a space X. Well, I'll write this R sub G of X. And it's going to be, by definitions, homomorphisms from the fundamental group of X into G. Here's an example. I think RG of, so this will be the torus that we all know and love. This is going to be, well, it's going to be homomorphisms from the fundamental group of the torus, just C squared into G. Right? These homomorphisms are just determined by what is in the generators here. So this is going to look like pairs with elements in G, but because here it commutes, there they need to commute to. So it'll look like this collection. Okay. So the representation variety has an action. Right, and what does this do if I take G, little g, acting on rho? Well, this will just send some element of the fundamental group to G under rho, G inverse. Okay. So this is an action by conjugation, and if I'm thinking of these things as eventually representations, this is like a change of basis. So it's maybe something we want to quotient out by. What we'll do is we can take the GIT quotient to get a smaller variety. Okay. And why I'm going to be taking a fancy quotient. I'll explain what it is. But basically the reason I would do this is that if if I just take the naive quotient, this is pretty poorly behaved. In general, so Hausdorff, if the action isn't perfect, then it should be bad. So what are we going to do is we'll take the Stanzier quotient and I'll define it for you in just the affine case. What does it look like? So what we're going to do is we're going to look at the ring of functions. So if I have V at some affine, let's say variety, and G acting on V, then I also get G acting on here. This is my notation for those functions on V. And so what I'll do, and so what is this looking like? This is f of x equals f of the inverse acting on x. So I get a new action. And here's my definition. V, I'll use 2 bars here. This is going to be the spectrum of O of V of V. Which is to say, the spectrum is a way of taking a ring and saying, I want the space, these functions on this ring. So the important thing for us will be that the functions on the GIT quotient will be this invariant subring. So this is invariant subring.
Here G is relative.
Yes.
So G in particular is an affine variety. So your representation variety is affine.
Yeah.
It's already affine.
I think so. Yeah.
So why you
Because
distinguish?
we want to reduce the He's asking, so yeah. So he was asking the question that, so the representation variety, it's actually not that bad. So why would you take the quotient? Yeah, sometimes it can be better behaved, right? And one reason in Skein theory you would think about the quotient is it'll turn out that character varieties, functions on character varieties are described by, here, after you take the quotient, you're talking about the Skein algebra. But before you take the quotient, you need like the internal Skein algebra.
Yeah, I mean, I know. I mean, it need to take quotient, but I mean, representation variety is already affine. So why you say take a GIT quotient for?
Yeah, I mean, it's just, yeah. I'm giving the definition in the affine version because that's what we need. Yeah. So the G character variety X, I'll write it X. This is going to be just G representation variety after this GIT quotient. Okay. And then sometimes we want to work with stacks. I won't highlight that much, but you would just take a stack quotient instead if you need this. Okay. Let's say what's the connection to skeins? So the connection to skeins is exactly, we see it when we start looking at functions on this character variety. right? And when I start to describe this, we'll say, well, first off, by definition, these are functions on the representation variety. Oops. Yeah. So we're here for the connection to skeins. Now we need surfaces for this part of the story. So sigma, sigma. So let's start thinking about the functions on the character variety. And these, in particular, I'm going to be thinking about functions on this whole larger representation variety. And I'll just at the end check that I have only the invariant ones. Okay, so how would we start building functions like this, right? So the representation variety is already some Hom space, right? So if I want a function on a Hom space, there's like a nice first thing to try. That's evaluation, right? So the first thing I'll consider is evaluation maps. Just to say something that looks like rho gets sent to rho gamma. Right, so this is maybe a function I'll call gamma hat, right? But here, what this is giving me is this is a function from Rg of sigma to G, right? And when the type of functions I want to think about here is I want ones that actually land in C. So I'm not done. I don't even have the type of function that I want to think about yet. And the second half of this procedure will be to take a trace. Right? So G is a reductive group. I often think of them as matrices, right? But I need to make that precise. So what I'll do is I'll do a trace along some representation. So what's that mean? I'll take G, the morphisms of some vector space, and then, so maybe, yeah. After that, I can go to C with just trace. And take the trace of my representation. And we see here, the trace is invariant under conjugation, right? So I am not just getting a function on the representation variety, but on the character variety, because it is G invariant. So let's give this all together. This function that would go from here, to here, to here, to here. Let's just call this tau gamma b, like this. So now we kind of get the nice connection to representation theory, or sorry, to Skein theory, because the idea is that these are rep G skeins. I mean, that's a crazy thing to say, but let's picture what's going on here. That's the data of one of these functions, right? So I have my sigma, and I've picked some element of the fundamental group here, right? So let's just think it's a curve like this. I'm not thinking about base points, although it's scandalous. And I also needed to pick this representation, so I have the data of a curve colored by some representation. So it's exactly the type of object they were thinking about before. If we have two of these functions, and I multiply them together, what I can think is going on is just, well, maybe I have two curves like this. This is colored by some W. But here, I'm thinking about complex value functions. So my Skein relation is, I'm going to keep the colors. So if I do blue and under it red, this is the same as red. Under it blue. right? Because I don't have any sort of ordering data that I need. And then what's my other relation that I would get is, what if we have a contractible loop, right? Something like this that I can retract back to nothing. Then what do I get? Well, I get that tau, so let's say this thing is gamma. I get that tau gamma colored by some v, a representation. This is going to be equal to trace of the long v of that representation just on the identity element in the fundamental group. So this is going to be trace of v of the identity matrix, and this is going to be the dimension of v. So the other relation that I get from this is that if I just have a contractible loop, this is going to be equal to the dimension of v. So bringing this all together, I'll call it a theorem, but there's a lot of work by a lot of people. I'm sure I've forgotten a few because it's been a big project for giving all the different parts of this, is that this in algebra for rep QG of a surface is a deformation quantization. Of this ring of functions. Okay, so there's this. There's another theorem by, I'll write down the, Lindsay has this number. You also need some results from the thesis of Julia. Is that if I look at the Skein category, rep QG with sigma, this is, sorry, I'm just rep G. This is the category of quasi-coherent sheaves on the character stack. So here's the stack. And you need the stack here for some excision stuff. So what this means is that and Julia already brought up this point in her talk last night, is if I put Q here, then what I get is a deformation quantization for this category of quasi-coherent sheaves. So this is the geometry we've been working towards. And the last thing I want to say today, tomorrow I want to talk about how we use this to actually quantize something. What I want to do, the last thing I want to talk about now though, is what about gates? What's going on with these gates geometrically? So, these were built from, I had some D embedding into sigma, right? In the classical setting, what this is going to give me is something that's going to be rep G, because the disk always gives me back whatever my coefficient category is. Here there's more geometric reason. Thinking about this, this is quasi-coherent sheaves on the stack, a point with a G action. And it's going to go from there to the quasi-coherent sheaves on the character stack. Sigma. Like this. And here's a fact. This is pullback along the restriction map. So what this be is should be about like this. And then here's so maybe fact 1, fact 2. It's got a joint, right, which I will need to make my internal Skein algebra, which I like quite a bit, is going to be just the push forward along that same map. So what's going to go on, what's happening, is that my internal Skein algebra for rep G of my surface, well, this will be rho low, rho high of the identity. So what is this identity? Where is this? This is going to be the identity here. No, here. So this is going to look like the structure sheet. So this will be rho lower star of the structure sheet. And then so when I pull it back, I will get the structure sheet on this character already. So this is something called the structure sheet. The important thing for us to know is it's the unit, there's the monoidal unit here. And this is going to be inside rep G now, right? Because that's the category I end up in. So what's this? What does this mean at all? So what we see is that when I take the internal Skein algebra construction and I just plug in rep G, what I'm going to get is, so this I took this, then I evaluate it on 1. So sorry, I guess once I evaluate it on 1, I'll get this because that was how I made my internal Skein algebra. So what I'll see is I'll get functions on this with an extra G action. And this extra G action is what we might call a framing. So this is what this is how our gates really manifested, and this is the sort of thing that if you have a geometric construction, you want to quantize it. This is what internal Skein algebras are doing for you. Okay. Cool. I think next I want to talk about what the parabolic defect quantizes, but not in 2 minutes. So I'll do that at the start of the next lecture.